Hi, let us proceed with our discussions about torsional force. You know that when a member is subjected to torsional force, torsion crack will happen. In order to control the torsion crack, you need reinforcement. This includes the longitudinal bar as well as the shear link. This reinforcement bridges the crack that acts spirally along the member. In terms of the working mechanism, even though the section is solid throughout, the resistance to torsions it will be more or less same as a thin wall box section, with shear flow developed within the thickness. The contributions of the middle part here it will be very minimal. This forms a analogical truss model where the reinforcement contribute in tensile resistance and the concrete performing as the compressive strut. Based on the model, failure of a member due to torsion is due to either the failure of the reinforcement or the failure of the concrete. Of course, concrete is brittle. Compressive failure of this compressive strut, it will lead to a brittle failure. Therefore, it is necessary to ensure that the concrete strength should not be less than the resistance provided by the reinforcement. We mentioned about an equivalent hollow section with shear flow developed within it. Shear flow is calculated by multiplying the shear stress with the thickness. This thickness here represents the effective thickness of the hollow section. The formula to calculate the effective thickness is given here. It is a ratio of the gross area divided by its perimeter. In our previous videos, we talked about the process to determine the effective thickness. There are two circumstances. First, it is the solid section. Assuming the internal part contribute minimal to the torsional resistance, this part will be ignored. Use this formula to calculate the effective thickness. Now, in the case that this section is actually hollow itself, you have additional considerations on top of the formulas to determine the effective thickness. First, your actual thickness must be at least greater than the calculated effective thickness. Second, your effective thickness needs to be at least 2 times the concrete cover. I believe these 2 times of concrete cover is a mechanism for you to ensure appropriate bond between the reinforcement and the concrete so that this truss model is valid. As for the actual thickness, if the actual thickness is less than the effective thickness, I believe the functions of the resistance to the torsions, it will be affected. Therefore, if these two conditions are not fulfilled, you will need to redesign the hollow section. Make it thicker at least, so that these two conditions are fulfilled. Done the shear flow. Let us look at the effective area of the box section. Don't confuse with the gross area. The effective area AK is calculated on basis of the center line of the effective thickness, which you need to get this distance multiply this distance instead of using B multiply H. You have half of the effective thickness one side and another half on the other side. That's why your B need to be minus with the effective thickness. You will do the same for the height. Half of the effective thickness on top and half of the effective thickness at the bottom. That's why you have H minus effective thickness. From here, you can work out the applied torque. Next, let us look at the truss model here. If you view from the side, it looks something like this. Now, if you view from the front, it looks something like this. The Q here represents the shear flow, which is acting in the vertical manner. The shear flow means the shear force per unit length. When you view from the side of the member, assuming this shear force here is an external force acting onto the truss model. Converting this shear flow into the total shear force, you will need to multiply with the mu k, which is the circumferences of this box section. To be more specific, we are not talking about these circumferences. Instead, we are talking about these circumferences, which is calculated on the basis of the center line of the equivalent box section. Now, taking this as an example, the mu k here, it will be equals to 2 times the B minus effective thickness plus 2 times the H minus effective thickness. This will be the force acting upward. And then the reinforcement and the concrete here forms a imaginary truss model. Reinforcement is subjected to tension, whereas the diagonal strut acts as the compressive member. Based on the amount of reinforcement bar provided, you are able to determine the tensile force in the reinforcement. This is the formula, which is basically calculated by multiplying the area of the reinforcement with the design yield strength. Don't forget to divide with the partial factor of safety of the steel, which Eurocode state equals to 1.15. Now that you have the forces in the steel, and you have the force here, this forms a right angle triangle. The vertical component here represents the vertical forces due to the shear flow. The horizontal component here represents the forces in the steel. The angle here represents the angle of the compressive strut. Now you can play around with trigonometry. Tangent theta here, it will be equals to the vertical component divided by the horizontal component. The vertical component is this, and the horizontal component is this. If you rearrange this, this is what you get. Now you have the circumferences. You also have the shear flow. Rearrange this formula, you get the applied torque divided by 2ak. Substitute this into the formula. Rearrange the formula here. Move the forces to one side and move the tangent theta on the other side. Substitute the whole thing here into here. Then you get this formula. This will be the formula that you use to determine the longitudinal reinforcement resisting the torsional force. Now, as far as this diagram is concerned, we are actually designing the longitudinal reinforcement. The link for torsional resistance, we will discuss it in our next video. Stay tuned.